in our WRRC seminar series for the fall. I'm happy to introduce you to Martyn Clark. He is a professor of hydrology at the University of Saskatchewan. Originally from Christchurch, New Zealand, he earned his PhD in geography at the University of Colorado Boulder and has worked for a time at NCAR and is now the Associate Director of the University of Saskatchewan's Center for Hydrology and the Canmore Cold Water Laboratory. He was also elevated to the prestigious position of American Geophysical Union Fellow. And Martyn's research is focused in three main areas. One, developing and evaluating process-based hydrologic models. Two, understanding the sensitivity of water resources to climate variability and change. And three, developing the next generation stream flow forecasting systems. Since receiving his PhD in 1998, Martyn has authored or co-authored over 200 journal articles. And today he will be talking about hydrological predictions from hill slopes to continents. And with that, Martyn, if you'd like to take it away.
Okay, very good. It's nice to be here. Thank you for inviting me. As I think some of you may know, we've had some collaborations with Tom's group in the past. We did a lot of work at NCAR on hydrological predictions over the contiguous United States. And then we realized or were told that we were missing some important states. We were missing Alaska and Hawaii. So we had a project to focus on Alaska and Hawaii. That's where we collaborated with Tom's group. It's nice to see Ryan Longman here. And I was looking, Tom, I think we published like 6 or 7 papers during that period, and I'll cover a couple of them today. And some of the work that we've done more recently that builds on some of the work that we did in Hawaii. So thanks for inviting me. The funding background that we have that's supporting a lot of our work now is the Global Water Futures Program. So this is touted as the largest university-led research program in the world. If you count the federal funding, it's about like 75 million Canadian dollars, and then the cost contributions, from other agencies brings it up to about 250 million. So it's covering a large number of different areas. In the most general sense, it's to place Canada as a global leader for water science in cold regions. Canada's really been there for a long time anyway. And then the main applications area is to address the strategic needs of the Canadian economy in adapting to change and managing the risks of uncertain futures and extreme events. This is a photo of the GWF director, John Pomeroy. Where I fit into the GWF program is one of the co-leads of the core modeling program, along with Al Petronero and our core modeling coordinator, Prabin Rakaya. In GWF Core Modelling, we have a number of themes, different areas: spatial meteorological data, geospatial intelligence, current generation hydrological modelling, so that's using the current suite of models to produce climate impact assessments. Next generation hydrological models, really like pushing the limits of what we can do in the hydrological modeling frameworks, water quality modeling, water resources modeling, hydroeconomics, and hydrological forecasting. So in these research themes, we've got 31 faculty, 33 research personnel who are primarily postdocs, and 21 collaborators from different parts of the world. And when I moved from the US to Canada, I was super interested in large domain hydrological modeling, and I picked as my initial modeling domain the North American continent. There's 2 main reasons for this. Part of the reason is collaboration, so that we can bring people, north and south of the border to be able to make more fundamental advances in large domain hydrological modeling. And the other is, it's a little bit selfish, I admit, it's the impact, because we thought that we could make a bigger contribution to the global science community if we included the United States as part of our modeling domain. As part of Global Water Futures, putting the G into Global Water Futures is our Planetary Water Prediction Initiative. So that's to exploit GWF science advances to improve our understanding and predictions of the global hydrological cycle. So part of that is to build the computational infrastructure that we need to configure and run our models anywhere on the planet. And the second is develop regional models in key areas where we've got strong collaborations. That's mostly in cold regions. So what I wanted to talk about today is just some of the work, just kind of a smattering of the work that we're doing and some of the core modeling themes. I wanted to talk about some of the work that we've been doing in spatial meteorological forcing data. So this overlaps most strongly with some of the collaborations that we had in Hawaii. I want to talk about some of our work on geospatial intelligence, some of our work on developing next generation hydrological models, work on river routing and water resources modeling, and summarize and provide an outlook at the end. So when we're thinking about spatial meteorological forcing data, one of the things that's really important when we're getting started is to fill any gaps that we may have in our station data sets. We've looked at this quite carefully, and I know Ryan Longman showed this in one of his papers, I think it was your 2018 paper, is that if you rely on the cross correlation between the stations themselves and fill the gaps in the stations, then you can reduce a lot of the temporal inhomogeneities that you have in the station network and substantially improve your gridded climate estimates. So what we did is we produced a 40-year gapless precipitation and temperature data set for about 27,000 stations across North America. We called that SCDNA. It's the serially complete data set for North America. And we've published this and we've made it available publicly. So you can just download the data set from that Zenodo link if you want to. The key difference here compared to some of the work that we've done in this space before is that the lead author here, Go-Chung Tang, developed 16 different gap filling strategies. So some of it's based on some of the simple methods that we've used before, like quantile mapping or spatial interpolation, things like that. But he also included some machine learning algorithms in there and some multi-method merging strategies. So the method that we followed here is we subject each station to comprehensive quality control. So a lot of the individual data sets that we used had some quality control there. But different data sets had different quality control. So we wanted uniform quality control applied to all of the data sets. We applied 16 different infilling and reconstruction strategies. We provided independent validation through split sample techniques. That's fairly standard there. And then corrected any climatological biases and compared to some benchmark data sets. So that paper's there, if you want to look at the methods. I think a lot of the methodological advances that we had in that data set are very applicable in Hawaii. Our main goal, however, was not to get station data sets, is that we wanted spatially distributed meteorological forcing data to force our hydrological models. And we've done this before, and including in Hawaii, but I want to highlight some of the key differences that we have compared to our CONUS work, our Hawaii work versus what we're doing in North America. What I'm showing in this plot, or what Go-Chung is really showing in this plot, is the distance that you need to go before you get one station, 20 stations or 30 stations for temperature and precipitation. And if you look at the rightmost plots, you can see that in the northern part of the domain, we may have to go 400 kilometers or 500 kilometers before we get 30 stations in the surrounding area of the grid box. So that means that it's really, really challenging to estimate precipitation and temperature given the very, very sparse station network. Our approach has always been probabilistic interpolation. So we're interested in providing an ensemble of precipitation and temperature so that we can explicitly characterize the uncertainty that we have in the spatial interpolations. Part of the uncertainty comes from errors in the individual station measurements, and part of the uncertainty comes from the poor representative that we may have of the station network. So we've done this in the past, and I apologize, Tom and Ryan, this will be old work for you. We've had station-based estimates in different data sets. Our key paper for this was for the contiguous United States. So that's Newman et al. 2015. So that's building on the work that I'd published with Drew Slater in 2006. Then the Hawaii dataset, we actually had a couple of papers in Hawaii, which is Newman et al. 2019. And that's a 1 kilometer grid over Hawaii for the time period 1990 to 2014. And then we did some work in Alaska and the Yukon as well. That's on a 12 kilometer grid for the time period 1980 to 2012. So the key innovation here is that all of the previous data sets were station-based data sets. So, we had that methodology sorted out. But what we wanted to do is merge the station data sets with reanalysis information so that we could provide better estimates in some of the more sparsely gauged areas. So we've got the approach to produce some serially complete data set for North America. And then we're using that to provide spatial maps of precipitation, temperature, and the probability of precipitation. We're using the reanalysis data, downscaling that, and using Bayesian model averaging to provide better estimates to combine the best attributes of the 3 different reanalysis products that we were using. Then we use optimal interpolation to merge the reanalysis data and the station data. And then EMDNA, that's the Ensemble Meteorological Dataset for North America, and we use spatially correlated random numbers to sample from the merged estimates of precipitation, temperature, and the probability of precipitation to get 100 ensemble members at a 0.1 degree grid across North America. So we're using these ensemble members to force our hydrological models so that we can characterize the impact of uncertainty in the meteorological forcing data sets on the hydrological simulations. So this data set's been published as well. We also published that in Earth System Science and Data. So here's just an example of different ensemble members that we have across North America. We've done some probabilistic evaluation of this data set. Here we're looking at discrimination and reliability for different precipitation thresholds. So discrimination is looking at the cases where an event occurs or an event does not occur if precipitation is below a threshold or above a threshold, and looks at the difference between those PDFs for when event occurs and event doesn't occur. So you want to have some separation there. And then reliability is looking at the average of the observed probability for different, the observed relative frequency for different probability bins. And what we're seeing here is discrimination and reliability. The upper left 2 plots are for precipitation greater than 0. The lower 2 plots are precipitation greater than 10 millimeters. The upper right 2 plots are precipitation greater than 25 millimeters, and the lower right 2 plots are precipitation greater than 50 millimeters. So we're seeing that we're generally getting pretty good reliability. You want the reliability estimates to be close to the 1-to-1 line. And then we're also getting fairly good separation between the 2 PDFs, and so that we're able to discriminate between different events. So we're interested in pushing this forward. So based on this work, Go-Chung developed SC Earth, which is the serially complete data set for a small planet. So that's now applied to a number of stations worldwide, providing serially complete estimates of precipitation, mean temperature, temperature range, dew point temperature, and wind speed. That paper is published in the Journal of Climate. And now we've also got EM Earth, and that's still under review. We've got minor revisions from BAMS, so we expect that paper to come out soon. Fingers crossed. You never know these days. And that provides ensemble estimates for the entire planet. So another theme that we've been working on is geospatial intelligence. And we see that while models have got similar data requirements, they're often configured in an individualistic and ad hoc way. So there's been a number of commentary papers on this. This is one example paper from Water Resources Research. It's asking the question, most computational hydrology is not reproducible, so is it really science? When we're looking at different modeling groups, they've got similar data requirements. They're using information on topography, vegetation, soils, some delineation of the river networks, etc. And they're all, sharing a lot of methods that are used to produce the underlying configuration data sets, but they're not sharing the code. They're all doing it in their own way. So we were trying to unify this a little bit. Here's an example that we have for North American setup for one of the models that my group's developed, SUMMA. So we have disaggregated the North American continent to about 500,000 catchments in the Merit Hydro data set. And each of those catchments require information on topography, soil, vegetation and land use, meteorological forcing data, and the river network. So if we look at what we can begin to get from some of these global data sets, so this global data set, the latest DEM, or the latest and greatest DEM, is the Merit DEM by Dai Yamazaki in Japan. And the folks at Princeton delineated the Merit DEM into catchments using a flow accumulation threshold of about 25 square kilometers. So that's what gives us about 500,000 catchments across North America. If we begin to zoom in a little bit and see what we're doing, this is an example of the Saskatchewan River Basin. Sorry, I was clicking in the wrong way. And then zooming in, this is zooming in the magenta region is the Bow River above Calgary, and this is getting to where we're located in Canmore. Zooming in a little bit more, so this is Calgary here, the Bow River coming up. And then if we zoom in even more, this is the Bow River at Banff. So Canmore is about 30 kilometers east of this point here. So remarkable degree of spatial information that we can get to begin to configure our models across large geographical domains. When we're interested in processing the catchment attributes, a number of steps which are common across models, downloading the shape files, delineating the coastal hill slopes, projection conversions, calculating catchment area, etc. When we're working with the soils data, the number of steps, downloading the soil grids data, converting sand, silt, clay content to soil classes, finding the mode, intersecting basin shapes in the soil data, etc. Similar steps for vegetation, getting the data and processing the vegetation data in the way that it can be used in a model. Forcing data. So this is an example where we're just running out models with the ERA 5 data showing maps of wind speed and solar radiation over North America. Number of steps that we're going through there. And then delineating the river network so that we can use network-based routed models in our model domain. When we put this all together, we've got the different steps, basin delineation, digital elevation data, soils data, vegetation data, meteorological data, river networks, etc. You can see that most of this workflow, all apart, from the bottom row, is model agnostic. So it can be applied, it's tasks that are required for any model configuration. And then we've just got a couple of steps at the end, which are model specific. This is work that Wouter Knurben has been doing, as part of our group. So what we've done is we've generalized this framework and applied it to a single model, the SUMMA model. And our next step is to try and take this generalized framework and apply it to multiple hydrological models. There's some fairly important philosophy that's underlying all of this. our practical goal is to improve the efficiency of continental domain model implementation tasks in order to make it easier to collaborate, easier to keep track of the work for reporting, paper reviews, increase transparency, reproducibility, code reuse, etc. So we've got all of these tasks. We've got them all documented nicely in GitHub repositories, etc., so that other people can use it. But the main philosophical motivation for this work is that we're really trying to advance the paradigm of community hydrological modeling rather than a community hydrological model. And the distinction may seem really, really subtle, but it's not. So for a long time, the hydrology community has been thinking about, well, can we all converge around a single model, an Uber model that can solve all of the world's problems? And that was really, really difficult because different modeling groups, had different models that were used for different applications. So there's not much traction there. But what we do know is that a lot of the modeling groups have got similar challenges, so we can do a much better job of sharing code and concepts across different model development groups. So that's really the paradigm of community hydrological modeling, thinking about the entire model ecosystem and how we can formalize and standardize a lot of our model configuration tasks to move more towards a community paradigm. So we're hoping that our work in this space is beginning to make some advances there. I want to talk a little bit about next generation hydrological modeling. So what we're interested in here is, on the one hand, multi-scale, multi-physics modeling capabilities. So we know that the equations that we have in our model are quite uncertain. There's gaps in our theory, gaps in our data, etc. And that we can characterize that uncertainty by having multiple different process representations. So we want flexibility in the way that we represent processes. And we also want to have flexibility in the way that we represent the spatial discretization of the landscape. So how do we discretize the landscape into subbasins? Do we have hydrologically similar areas across the landscape that we can lump together into hydrological response units, etc. And have models that are capable of simulating all of the dominant processes from headwaters to estuaries and the top of the canopy to the depth of active bedrock. So that's kind of the model development side. And then the coupling workflow infrastructure is intra-component coupling, where we'd be adding new capabilities to an existing model, intercomponent coupling that manages the exchange of information for different model components, multi-model coupling, workflow management, etc. So I'll give some examples of what I mean here. This is an example of a model that's been developed in Canada. It's the Canadian hydrological model. The key attribute of this model is its unstructured triangular mesh, depending on topography, vegetation complexity, etc., to provide a nice way to simulate primarily blowing snow processes across complex terrain and snow canopy interactions. So this is, one thread of what we've got here. And this figure here, may be a little bit foreign for a group in Hawaii. Maybe it would be relevant if you're thinking about processes and on the top of Haleakala, maybe 1 or 2 days a year. What I'm showing here are different simulations with CHM. This is work by Vincent Vianney, where we've got no spatial redistribution of snow, so no blowing snow. And the snow is somewhat smeared across the landscape, where we do have spatial redistribution of snow in the middle, and the LiDAR data. So this is kind of a process denial experiment where we're saying, well, to what extent do our hydrology simulations degrade if we exclude one of the dominant processes? So the dominant process here is scouring of snow from the exposed ridges and deposition of snow in the sheltered areas of the landscape. And this here is showing that it's critical to represent the observed snow patterns by incorporating those dominant blowing snow processes. Where we're going with this is kind of fairly large. So we're thinking about the traditional Earth system model coupler. So in this coupler, we may have a land model, atmosphere model, ocean model, sea ice model that are all talking to each other as part of the Earth system model coupler. But what we're interested in is having a hierarchical coupling strategy where we break that down more. So we've got a land model coupler that may have a glacier component, a biogeophysics component, biogeochemistry component, rivers and lakes component, groundwater component, etc. And then within one of the biogeophysics components, we may have a model that's further disaggregated into process domains like vegetation, snow, soil, or thermodynamics, hydrology, etc. So the innovations that we're adding here is that we've got a combination of intercomponent and intracomponent coupling. So it allows us to incorporate physical processes at various levels of granularity. So one level of granularity could be an individual equation that has a flux parameterization. Another level of granularity could be an entire land model. We include the numerical solution as part of the couplers, and the traditional couplers, they're often running the individual component models at the smallest time step that's necessary, and the time steps are constant in space and time. If we include the numerical solution as part of the coupler, then we can have numerical estimates of the splitting error and then control that splitting error through adaptive substepping strategies. And then within the model component, so this is the herendogram for the SUMMA model that I've put together. We also have a hierarchical structure where we define the model architecture, which is the selection and arrangement of state variables, the model parameterizations, which are the functions that we use to describe the relationship between the model states and fluxes, and the model parameters, which are the adjustable coefficients in the model equations. So when we construct the model, we've been very, very careful to follow best practices in computer science on separation of concerns. So we separate the model physics from the numerical solution so that we can use third-party solvers, have modularity at the level of model fluxes, so provide some standards there that simplifies sharing of the code and concepts across different model development groups, and organize the overall code structure, initialize, run, finalize, etc., to simplify some of the integration that we need with other frameworks. Beyond the land model, we've been looking at river routing and water resources modeling. So our river routing model has been the mizuRoute model. So this is something that I worked on in New Zealand between 2006 and 2010, which was part of the TopNet hydrological model. When I came to NCAR, we just took the routing component out because we thought that our models would be easier to apply when they were constructed in a more modular way. And we applied it to larger geographical domains, and we called it mizuRoute. So this is the work that's led by Naoki Mizukami, who's still at NCAR. And he's got two papers there. The first is in Geoscientific Model Development, published in 2016. And a second paper, it says under review there, it's published in James, but it actually came out just a couple of months ago. The funny thing here, you know, if you want to, is mizu means water in Japanese, and mizu is also the part of Naoki's first name, so we thought that would be a good name for the model. So what we're doing is we're starting with the HRU average runoff. So the HRU is the hydrological response unit. And then we're routing that across the hillslope to the HRU outlets. That's just done using simple unit hydrograph type approaches. And then we're routing the water through the digital river network, through river reach routing, a few different approaches that we have there to provide stream flow at multiple different points across the river network. The key challenge that we had when incorporating mizuRoute into Earth system modeling capabilities was parallelizing the hierarchical river networks. So, and we've got a tree-like river network. There's clear dependencies between the downstream elements of the river network and the upstream elements of the river network. So we had a few key objectives. The first was to balance the computational load across processes and to minimize communication costs across processes. So our approach there was that we were keeping some of the smaller tributaries on the main stem processor. So we had a master node which was handling the main stem. The grey river network, the grey parts of the digital river network there are handled by the main stem processor, so we don't have to communicate the information. And then all of the bigger tributaries were farmed out to independent processors. So we only needed to communicate information from the outlet of the bigger tributaries to the main stem. So here's an example here of, this is the Mississippi Basin, actually, that's disaggregated into 4 domains, 8 domains, 16 domains, etc. So we also had a further level of discretization where each of those tributaries were discretized in similar ways, but using shared memory approaches. So within tributary parallelization was handled with OpenMP, and the between tributary parallelization was handled using MPI. So here's an example of the 4 tributaries in the Mississippi River Basin. So we've got all of the small tributaries on the master node, so that they don't need to be communicated. And the red, cyan, and magenta basins are handled by different processors, and each of those bigger basins are further parallelized using OpenMP. Some of our results here when we're looking at MIRROT Hydro for global river routing applications, we're looking at scaling. So we've got a scatter plot where the x-axis is the number of processors that we're using in our high performance computing facilities, and on the y-axis is the elapsed time per routing time step. The dotted gray lines represent perfect scaling. When we're on the global domain, we're getting close to perfect scaling, and that's because we've got a lot of independent river basins that are very, very easy to parallelize. When we're moving to the most challenging case, the Mississippi River Basin, this is an example where it's broken up into 16 domains. We're not getting perfect scaling because we've got computational bottlenecks at the main stem, because the water that's flowing down the main stem can't be processed until all of the upstream areas have been processed. So there's only so much gain that you can get from parallelization before throwing more computers at the problem begin to have a diminishing returns. We're also working on incorporating lakes and reservoirs into mizuRoute. So this is an example of streamflow simulations for the Mackenzie River Basin, showing the changes in streamflow throughout the digital river network, and also changes in lake level. We're looking at some of the individual lakes, comparing observed and simulated lake levels. Some of the simulations are beginning to get into the right ballpark. This is something that we're working on in earnest now, and model development that we're still in progress, really. So to summarize, what we're doing for hydrological prediction applications is that we're interested in forecasts on multiple timescales. So to produce a streamflow forecast, we go through a lot of the steps that we've talked about before, where we've got station data, reanalysis products that are interpolated spatially, across the landscape. Some data fusion, the example that I showed of optimal interpolation of station data networks and reanalysis products to produce spatial meteorological forcing data. The spatial meteorological forcing data is used as input to a process-based hydrological model. During the initialization period, when we have observations, we can assimilate those observations in the process-based hydrological model to improve our estimate of the initial hydrological states at the start of the forecast period. And for our historical simulation, we've got historical hydrological model simulations. When we're interested in predictions going into the future, we can use different methods at different forecast lead times. So we've initialized the model at the start of the forecast period. So that's the amount of snow in the basin, the amount of soil moisture in the basin, etc. And then if we're making forecasts out to a couple of days or 2 weeks, something like that, we've got numerical weather prediction models that are spatially downscaled to produce fine-scale meteorological forecasts that are used as input to a hydrological model. If we're interested in climate scenarios, we may have climate models that have got some bias correction step to provide climate scenarios that are used as input to a hydrological model. Then a hydrological model is used to produce hydrological forecasts or hydrological projections of change on decadal timescales. There may be some statistical post-processing of those forecasts or projections to produce prediction products. And the importance of initial conditions and meteorological forecasts obviously varies based on the region that you're in, the forecast initialization time, forecast lead time, etc. That all comes together as part of our hydrological prediction system. So if I summarize some of the things that we've talked about today, what we're doing in GWF Core Modelling has been developing computational infrastructure to enable large domain hydrological modeling. And we're developing deterministic and probabilistic forecasting capabilities. And we're taking a model-agnostic philosophy. We talked about the difference between community hydrological modeling rather than developing a community model, so that we can do a much better job of sharing code and concepts across different model development groups. And we're really interested in developing state-of-the-art capabilities and predicting terrestrial water, energy, and biogeochemical cycles. It's a wicked interdisciplinary problem. We're trying to make predictions anywhere on the planet, a range of different environments, and where there's different controls of vegetation processes, snow processes, groundwater processes, etc. So it's a big problem. It's much bigger than we can handle ourselves. So I'm really looking forward to collaborations and hoping that this talk will spawn some future collaborations between the work that we're doing and the work that you're doing in Hawaii. So I'll leave things there, and thank you very much for inviting me.
Thank you, Martyn. I want to open the floor to any questions. I didn't see any in the chat, but people are free to unmute and ask questions now. Aurora, I see a raised hand.
Hi, yeah, thanks for that. I guess I was thinking about, in the context of Hawaii, where we're not, we're definitely much more straightforward river stream networks, but also, yeah, much smaller spatial scale. What do you see as sort of the capacity or limitations of having applying that framework, but at very local, much smaller spatial scales that we're working at? And maybe that's a question for sort of both Tom and Martyn together. Because there's the forcing issues in getting those sort of spatial products at the appropriate spatial scales, but we're also facing challenges, I think, with our catchment, like how well do we understand our catchments, and then thinking about those fine scale processes we were talking about, snow and blow. We don't have that, but maybe we have to think about cloud mountain interactions or fog mountain interactions, with the goal of thinking what would we need to be able to predict future stream flow in Hawaii. So sorry, that was a how do we take what you just described for our Hawaii and or Pacific Islands context, and what do you see as the major sort of connections or gaps?
Yeah, so for a lot of these global data sets, they're developed using global products that don't have a lot of the spatial detail that you need for local applications. So what we're viewing them as really a starting point if you're interested in global local applications, and gradually adding more local detail, when you have it. So even for the work that we're doing in the Canadian Rockies, we find the flow accumulation threshold of 25 square kilometers to be much too coarse. And we've got other versions of these data products that are using flow accumulation thresholds of 1 kilometre, which are much more important and much more appropriate to resolve some of the topographic gradients that we have in some of these basins. Beyond that, if you've got better DEM information, then you can do the network delineation yourself and provide more of the spatial detail that's important. But the key problem that we have is with our understanding of the dominant hydrological processes and our capability to predict them. I think this is where we need to have much more dialogue between what people are doing in the large domain hydrological modelling community and the people who are working in individual catchments. So when we're looking across space, you've got a single model that's applied across a large geographical domain that's not going to have a lot of the dominant processes that are important everywhere. If it's been developed with people with an interest in snow, we'll have a lot of blowing snow processes, but may include some of the cloud water processes that you were talking about as being important in Hawaii. So the way that I view the interaction going is improving the theoretical underpinnings of our models. And I published a paper on that in 2016, where I was arguing that when we're talking about different models, often our discussion is, what's the difference in algorithms rather than what's the difference between algorithms and the processes that are actually occurring. So if you think about the steps in model building, where you might start with your perceptual understanding of the processes that are important, and have that qualitative description, there's a lot that you can do by able to say, well, okay, we've got this qualitative description of the dominant processes. How does that map on to what's actually included in the model? And then going through to simplifying your perceptual model into a conceptual model where you're beginning to define control volumes, and then really beginning to interrogate what some of the parameterizations of the individual fluxes are. So you can go through all of those stages, but I think that the part that's missing and is often neglected is at the perceptual stage as to what processes are really important and are they even included in the model. Because if you are not looking at that stage, then it's always going to be treating your mathematical model as a marionette to try and match the data without incorporating the processes that you know to be important.
And Martyn, thanks. Great talk. I wonder if you could comment on the work that you described and how it relates, how it differs, and how it will be used to help efforts such as the U.S. National Water Model, which is an application of Earth Hydro. So how do you see, what is your role of your group in helping, national level entities in improving and making better forecasts, hydrological forecasts, such as, National Water Center and the National Water Model?
So I'm speaking to you from Canada. So no official role, but I can talk about, how things are developing. The National Water Centre is in the middle of somewhat of a transformation at the moment, where WRRC Hydro was their initial modelling capabilities, and they're in the middle of what they're calling their next generation modelling project, which is developing a next generation set of hydrological modelling capabilities. And from what I've understood about that project through presentations that are available publicly, it's understanding that there's not going to be a single model that works well everywhere, and creating the capabilities to have a tapestry of different hydrological models that are being applied across different parts of the landscape. That's all done using the basic model interface framework that Scott Peckham developed in his work at Instar in Colorado, which enables you to put multiple models into the same framework and begin to have some of the interoperability that's important. a lot of what I'm talking about, you can think of it as like next generation modeling, or third generation modeling. Hierarchical process couplers doing a much better job with the numerical solution, being able to take advantage of heterogeneous computing capabilities to provide much more flexibility in the types of modeling approaches that can be applied across large geographical domains. So it's an active area, Tom. There's lots of scientific challenges associated with that. Large domain parameter estimation being a key challenge, where a lot of people are working on an individual basin scale, and can use standard calibration methods. It can be difficult to transfer parameters to ungauged basins and get consistent sets of parameters across large geographical domains. Data assimilation there's been a lot of progress on that, but that's still an unsolved problem with some challenges as to how you estimate the uncertainty in your models and observations, how you account for time lags in the hydrological system, things like that. So we're not there yet. Large domain models have been around for a long time, but there's tons and tons of challenges that need to be addressed in order to push this forward. I'm not sure, did that answer your question?
Yeah, I just wanted to hear a little bit about how it relates to efforts such as what we're going to be working on, possibly working on together in the Cairo, Cooperative Institute, and let other people know about that. So.
Mm-hmm.
I guess I joined a little bit late, so not sure if you touched on water quality issues, including sediment. And actually in Hawaii, we have some difficulties addressing, like small time scale sediment processes because of complications in soil profiles and subsurface geology, geography, geology, very steep slopes, and very hard to collect enough data, especially from important high-level areas. So what are your thoughts about such issues? That how can we handle these and get better simulation modeling?
Yeah, that's something that I'm just beginning to look at, and you didn't miss anything. I didn't talk about water quality at all. We've started a collaboration with a fellow at Environment and Climate Change Canada. His name's Diego Costa, and he's developed this framework called OpenWQ. So what Diego does for water quality is an approach to unify different approaches for water quality modeling in the same way that I've unified approaches for the way that we represent the biogeophysics. So moving forward, the first step is to build the computational infrastructure so that we can have a much more consistent way of dealing with the transformation and movement of the different constituents that we have within our system, and then being able to improve the physical representations. This is done in the land modeling community a lot with carbon, nitrogen, phosphorus, etc. But it's primarily focused on vegetation atmosphere interactions rather than the constituents, within the terrestrial, like the river part, rivers and lakes.
Okay, are there any other questions? All right, looks like there's no more questions.
I have one more question.
Oh.
Hey, Martyn, good to see you. Thanks for the presentation. I'm always amazed at how much you can get on a slide. It's really a skill, and I really enjoy seeing you present. I got a question about the EM Earth data set that you're going to be putting out. It's a probabilistic rainfall data set globally. Is that correct?
Yeah.
And have you used that? Have you obviously, or have you used that in the model yet, or what are your plans on doing with that? What do you expect? What kind of results do you expect from that? Incorporating that into the model?
Well, there's two kind of, yeah, we have used it in some models. So this is part of our Planetary Water Prediction Initiative, and there are two threads of that to develop the computational infrastructure that we need to run models anywhere. This first thread, and the second thread is model applications, for some key basins. So we've had some key basins in the Himalayas, and we've used EM-Earth for the forcing data for some of those basins, and found that it's provided some improvements over some of the other data products that were available. So that's kind of like where we've used it now. What we really want to do that we're super excited about is to use EM-Earth to understand how the meteorological uncertainty propagates into uncertainty in our simulation of hydrological processes across the globe. And because we have characterized the uncertainty quantitatively, and that we're fairly sure that the uncertainty estimates are statistically reliable, that allows us to make some statements as to where meteorological stations are most needed, and where the hydrological simulations are most uncertain because of the weaknesses that we have in the meteorological data networks. So that work's just really beginning. We don't even have presentations ready on that, but that's the research problem that we're beginning to address.
Syed, did you have a question? You turned your video on, so just checking. Okay.
No, thanks. It was clear to me. I appreciate it.
Okay. Before we go, Tom, did you want to add any closing remarks? Oh, you're on mute.
I just want to thank Martyn for that awesome presentation. It's great to see you, and thanks for sharing on all the important and really amazing work that you're doing at Canmore. And how grateful my group is to continue working with you and your group. We look forward to more years of that. I also want to thank everybody that's still here and all those who came earlier for joining this presentation, joining the seminar.